So we're back with the series where we sort of recreate this grad school project of mine, and I think last time we did a lot of progress with data. I see some data, I generated some data offline here, so we have train and validation data now. And I think we enabled actually full-scale training, if I remember correctly. Yes, I do. So I'm already on a new branch. Let's do a quick overview. Let's see if we have the diagram. We should have it here. Oh, here we go. Oh yeah, and we also did this data splitting logic last time. Because we ran out of RAM, I think, because the way NVIDIA implements their toolbox is not that great. Okay, so we have a bunch of data now. We know we can train a model. Let's see, where are we overall? Pretty good progress, I would say, overall, right? So we have diffusion training, signal processing, PyTorch, UV, pre-commit hooks by project. We don't have typing or logging. So there's a few more Pythonic things to do. We have a loss function. We have data generation. We're missing the big piece though, which is inverse problems and model inference, right? Like what are we going to do with this model? I think we talked about this somewhere in this diagram. We talked about here it is. We talked about the difference between training a score-based model and using it, which is also called inference with the score-based model or a diffusion model. So actually I'd like to implement this today. Sampling synthetic data, okay? From a score-based generative model. And we're gonna do it the way I did it in the paper, which starts from pure noise and is sort of supposed to produce synthetic data. And we're gonna monitor this. Well, we'll write a Python function. And we may also add some logic to monitor this during training, because you kind of want to see during training how does the quality of the generated data improve or stuff like that. Now in order to implement this, we're gonna need the paper. This is actually a bit trickier because it's not actually in the paper, right? So let's see, MIMO, where is it? Here it is. Channel estimation with score-based generative models. So now we actually don't have this type of sampling, pure synthetic data sampling. And last time we looked a lot at how the channels look like. But actually we sort of do have it here. So actually the update would be closer to equation 4. We don't really have an algorithm for it though. So what we're gonna do is we're gonna have to figure out, which may be tricky actually. It's probably easier to figure out what the parameters are, but we're gonna have to figure out, here it is. So this is the real update. We're just gonna cut this term though to not make it conditionally sampled. Okay, so we're just gonna leave the 3. So the current channel becomes sum alpha times the model prediction at the current channel plus some added noise back, which starts to make a lot of sense now actually. This is pretty close to this, right? So I start from pure noise, I pass it through the model. Remember the blue thing is the model here. I get the purified version, but then I add some noise back. The problem is we're gonna have to figure out what these constants are and what their schedule is. Let's see, what do we do in the paper here? What do we say? Oh, okay, so we have some formulas here. Okay, this is a lot closer. So we know it's square root 2 beta times some alphas. We know it's a geometric progression. So alpha I will decrease. R is less than 1, right? So the more I multiply with R, so alpha 0 is just alpha 0, alpha 1 is alpha 0 times R, alpha 2 is alpha 0 times R to the second. Okay, so we know there's some exponential thing here. There's also a sigma zi. which I don't remember. Let's see, it's hyperparameters discussion section 4. Yeah, so we're pretty close. But it's actually sigma. Okay, so I think we set sigma zi constant. Okay. Yeah, and that's it. This looks pretty much it. And then for the conditional sampling, we just have to implement this other term, and then that's also it. So maybe we can think about how to write this update rule maybe in a smarter way, so we don't have to write, we don't really need two functions, right? Doesn't look like we need two separate functions. So okay, so we just have to implement an update. So how should we write this? We're basically gonna implement this, right? Except we start from some oh no, sorry, this zi is also sigma zi. Okay, so we have to look, do we say what values we use, or are we gonna have to guess them? We may have to guess them, but we know how to guess them because we're gonna have training data, or we're gonna have validation data, so we can sort of visualize how the channels look like and if we get them right. Now let's try to find these in the paper though, section 5. I need an alpha, beta, and a sigma. This is not the same alpha. This is a bad where. Oh, here it is. So no, it's not this. No. Actually, we don't have details on the sigma. Is it the sigma? We also need to know what we trained the model on. Aha, it is. Oh, here it is. I see it. So sigma zi is a noise level selected uniformly at random from a set of values. Okay, so we need to build this set, and I'm pretty sure it's... Is it exponentially spaced or is it geometrically spaced? Yeah, oh, I see, here it is. Inference noise level, same as what S was trained with. Okay, so we can choose, okay, this is what I was looking for. So first we need to go and see what we trained this with, and then we need to descend on the noise levels, right? Because as I increases, the convention here is that as I increases, this power should decrease. Because towards the end of the or this is how it should be. I think that makes sense. So the first noise level is the highest. Yeah. Okay, and then we run inference exactly on these same noise levels, and then we repeat the step m times at the noise level, and then we descend on the noise level by just changing the sigma and also incrementing the alpha 0 coefficient. And the 2 beta is another multiplier for the noise, a separate one. Which can probably, honestly, this is just, well, I guess technically it can't be absorbed because this has to be exactly like in training, but yeah. Okay, so this is sort of what we have to do. So we have to do exactly this, except of course the numbers I made up here. So let's write a clearer picture of this then. Let's write something nicer, right? So we're gonna start noise, but it'll be Do I have a sigma here? No, I do not have. I'll just call it S. Actually, this is not great because I can't do math here. Yeah, so except this is just sigma Z0, SZ0, okay, times IID noise, okay? Then we're gonna add back, okay, so this is score-based model. So we do a forward pass, then we need to add back square root of 2b times a times r times SC1 times noise. Okay, we add this back. Then we repeat. Okay, so we need more accurate numbers here. So let's see. Then I go through the model again. No, that's not how I go, because I do a plus here actually, right? Because it says I sum them. Right, so I take the previous estimate and I sum both the noise. Okay, so it's a triple sum, right? Plus, plus, plus. I'm ignoring this conditional term, where that's the fourth term that we'll implement some other time. But just to get, okay, so it's a triple sum then. So this thing here actually goes here, and it also gets summed with this. Let me see here. How can I get this here? There we go. Now I just need a triple sum box, which can be something like this plus well, actually they should go in the node here. So this should go here and here. And that's it. This thing gets repeated now, okay? Because now I have my output, which is the output of the triple sum. Again, I go through the model, the same model now. And I get out. And I want to sum noise, except now the noise decreases a bit, and the only way it decreases is because it's times r to the power of 2 now, and SZ2. So there's a doubly, yeah, there is some fiddling to do here, right, with the constants. Yep, that's how it is, right? Because I sigma, yeah, I want to add less noise. Do I also anneal my step size? Let me look at the other paper we have then. Compressed MRI generative. I think we have better formulas here. Somehow I'm not happy with the formulas I wrote in my paper, or the paper which I did after this. Okay, this is with the fixed coefficient, so this is eta square root 2 eta. So maybe I'm overcomplicating it. Maybe it really is like this. Yeah, I think I am, because there is no beta. So beta is something I made up. So this should be 1. So then it's just... Oh, sorry, I forgot to multiply the score term. Oh, yeah. Sorry. So, okay. So beta is 1, so square root 2 times this. But where is the annealing part though? I wonder if I have too many coefficients. So there's also a multiplier here. I forgot, right? It's multiplied with, it seems like it's A times R in this case. And then it goes to the sum. Right. And now this becomes multiplied with A times R squared. Yeah, these coefficients are definitely in sync. Okay, so let's do the basic one. You know what? Maybe we just do the basic one. Then if it works, it works. If not, then we'll... Now my paper technically has... But I don't need to match the noise levels though? Like, is it SC... No, it is. Sorry. Okay, here it is. Okay, so no, this is right. Okay, so it's psi t here. This also decreases. Oh, okay, so we're good then. This is SE1, SE2. This also changes. Okay, so then B is just 1 by default. Okay, right, good. So then this also happens here. So then the input again goes here. And again, we get another estimate, and ... until we reach a very tiny SC. And then at the final step, we no longer add the noise, which I think there's detail I didn't actually implement. So this will be good. Yeah, we still add a bit of tiny noise in my paper in the original implementation, which I think is a mistake. Like, because at some point you reach ... and at the final noise level, let's see, can we get it? Yes, we can. So when you reach the final noise level, so this will be A times R to the N, you don't want to add noise anymore, okay? So this will be ... It continues this way, right? Because we don't have room to draw. And then we can call this final output data, right? So now we magically went from noise to data, right? Because we start from SC. Wherever I say times noise, that means unit power noise. So we're going to use torch ran then. And this is called annealed Langevin dynamics. Annealed, okay? So inference with annealed Langevin dynamics. Langevin dynamics itself is the process where you keep this constant, where you just add the same amount of noise. Actually, let's look that up. This is a good thing. I think the step size still... No, maybe it's... Yeah, so Langevin dynamics is just everything is constant. Or rather, the step size... Oh, no, sorry. The step size is constant. Okay, well, these are very hard to read. I wish we would find something. So it's one of the bases of score-based. Interesting. So even Wikipedia knows this, right? From Langevin dynamics, we have this differential equation where we multiply the gradient epsilon, which is the useful information, which in this case is given by the score-based model, plus square root of 2 times epsilon, which we recognize easily now, right? Right, because we multiply the useful info with A times R, and then square root of 2 times A times R, except I introduce my own beta here, which should kind of be 1, times ZI. Oh, okay, and the noise is constant, okay? So Langevin dynamics would just do times noise, and it would even keep the step constant. Like Langevin dynamics everything would just converge, but then maybe at the final step you still don't add noise there. But Well, we're doing the annealed version, right? Where we decrease our steps and the added noise power as we go along. So this kind of makes sense. Another optimization way to draw this, how should we think about it? Yeah, like if you're trying to maybe, let's see, I'm trying to try to draw some optimization here, which is going to be pretty hard actually, right? So let's say we're trying to optimize a surface like this, where the shade of green means a higher value. Okay. So then, and I start from somewhere here. Okay, and now I know the gradient points in this direction. Okay, so what I do is I take a gradient step. This is probably not the best drawing, but I take a gradient step which is scaled towards the direction. The surface is pretty easy though, because it points clearly towards the minimum. Assuming there's also a gradient of color. Then I take a scaled step in this direction. Then I add some noise, which kind of throws me around a circle. Okay? So when we say we add noise, okay, so we can say adding noise places us on a circle in high dimensional space. Let's call it a sphere then. On a hypersphere. Okay, around the original point. Okay, so then I start, so then I can say I started from init and I get to new. Because I land somewhere randomly. Okay, so this is step 1. Then I repeat the same thing. I take a gradient step of exactly the same step size, okay? It also happens to be pointing, it's got to point towards the center here, but of exactly the same. Then I throw myself on another circle. I may go back, I may not go back, etc., etc. Now, this is Langevin dynamics. Okay? So annealed Langevin dynamics okay, it kind of does the same thing, except it shrinks the step size and the circle radius after every step. Okay, so let's draw one more step here. So then let's say I do this thing again and I happen to land backwards, I don't know, somewhere here. Then I would take another gradient step of the same size but pointing towards my high value. Then I throw myself on another circle here. Okay, etc., etc. I eventually kind of make my way, right, in this noisy style. We can actually draw this picture in 2D, which is not a bad idea for a separate stream. And ... Okay, annealed Langevin dynamics would say something like, hey, I'm here. Okay, I throw myself on the circle. Then I'm gonna take a slightly smaller step. And I'm going to throw myself on a smaller circle. Oh, actually, I can do these two together then. Good. Whoops. Okay, so then I would maybe land, I don't know, here. Then we go again, even smaller step. Actually, why does it tie this? I don't want to tie it. And even smaller circle. And maybe I land somewhere else, etc., etc. Now here's the trick. If in a way this is noisier but faster, it's less noisier but can risk becoming too slow, right? You can see because these circles will shrink. At some point, I'm going to take steps so small that I'll just crawl my way to the maximum, right? And so the goal is maximize, i.e. get to darker shades of green. So this is why you can, but then if I pick my exponential rate and my initial step size in a smart way, you can also see that maybe it is better to do the annealed version, because I sort of laser down towards the end.